5.2. In this section, our goal here is to be able to evaluate and graph other polynomial functions. So some vocabulary. A polynomial is just a monomial or a sum of polynomials. Okay, so monomial meaning one, and all we need to do is sum or add a whole bunch of monomials. So like, for example, x to the second power plus 3x minus x to the fourth power. Okay, that's a polynomial. A polynomial function is just a function where the exponents are all whole numbers and the coefficients are all real numbers. So in order to be a function that's a polynomial, all the exponents have to be whole numbers. Can't have any negative exponents or variables as exponents, okay? Just regular whole number exponents. And the coefficients are all real numbers. Can't have any i's, okay, or imaginary numbers of any sort. Standard form of a polynomial function is to write the terms in descending order from left to right, okay? And when we say descending order, we're doing it by the exponents, okay? So we call that standard form, as if your exponents go from biggest to smallest, from left to right, okay? Our leading coefficient is the first term in standard form. The degree is the largest exponent we have in that polynomial function. And constants are just numbers or plain old numbers that have no variables attached to them. So here are the common types of polynomial functions in the first few chapters, like chapter 2 and chapter 4 that we just got done doing. We did linear equations, so lines, and then quadratics, which are the parabolas. So now we're going to get into bigger degree polynomials, so like the cubic functions and the quartic functions, okay? So the constants have no variable attached to them. So for example, negative 14 is just a constant line. A linear has a degree of 1, so only an exponent of 1. And then quadratics, we've seen, had exponents of 2s. That was the biggest degree we got. So cubics have degrees of 3, and then quartics have 4, and on and on and on. But these are the most common ones we see. So for example, we're going to see if this is a polynomial function or not. If it is, we're going to write it in standard form, state its degree, type, and leading coefficient. Okay, so just by looking here, I have whole number exponents 4, 2, and then 0, so that's good. And all of my coefficients are real numbers, so this means that it is a polynomial function. Okay, so this one is a polynomial function. So since it is, I'm going to put it in standard form. So big is the smallest exponent. So I got 4, 2, and 0. Well, it's already in standard form. And I'll just put SF for standard form. And I got to state its degree. Well, the degree is the biggest exponent. So my biggest exponent I got, that's 4. The type, well, if we refer back to that chart, the degrees of 4, these are the quartic polynomials. And then the leading coefficient, I'm just going to make LC for leading coefficient. Well, my leading coefficient is the line leader of all the coefficients in standard form. Since it's already in standard form, I look at the very front, my line leader coefficient is 1. So my leading coefficient is 1, and that's all I needed to do. If we look at another one here, we're going to do the same exact thing. Looking at the function g of x, well, I see exponent of 1 and of 2, and that has an exponent of none right now. Okay, so all my exponents are fine. Then if I look at my coefficients, I have 7, and the negative square root of 3, and pi. Even though pi is kind of a weird number, it is a real number though. Okay, so this one is a polynomial function, even though it looks kind of weird. So it is a polynomial function. So now I need to make sure it's in standard form. Okay. If I look here, my exponents are not going in descending order. So if I rewrite that, g of x, I'm going to put the highest exponent term first. That was pi x squared. Then what should go next is my exponent of 1, so 7x to the first power, minus my constant, or the negative square root of 3. So that's now in standard form. Okay, status degree, well, my degree is the biggest exponent. In this case, that is 2. The type, since my degree is 2, that is a quadratic function. And its leading coefficient, the line leader, the coefficients in standard form, well, that was pi. And pi was a real number. Another one here. Okay, if I go along here, I have exponents 2, negative 1, and regular 1. Well, right off the bat here, I see a negative 1. I can only have positive whole numbers for it to be a polynomial function. So since I automatically have that negative 1 there, it is not a polynomial function. Because that negative 1 is not a positive whole number. Okay? So since it's not a polynomial function, I don't need to go through and put it in standard form and tell the degree and type and all of that stuff. And the last one here, if I look at this one, okay, if I look across here, my exponent's 1, x, and 5. Okay? Well, I have an exponent of x. I can only have exponents of positive whole numbers, right? So automatically, this one's also not a polynomial function because of that variable as an exponent that we can't have. So this one's not a polynomial function. Okay. What we have next is direct substitution of a polynomial function. All that means is I'm going to take my x value and plug it directly in to every x I see. Okay, so my x is 3, so I'm going to evaluate my function at 3, so f of 3. And I'm just plugging in 3 for every x I see. Okay, so now I need to evaluate my exponents first according to PEMDAS, remember? Okay, so leave alone that beginning multiplier there, okay? So 3 to the 4th power is 81, minus 5, 3 to the 3rd power is 27, but negative 4 times 3, that's negative 12, plus 8. And now I can just simplify there. 2 times 81 is 162, minus 5 times 27, which is 135, minus 12, plus 8. And you can straight up plug that in the calculator and you'll get back 23. Okay, so we directly plugged in 3 to every x we've seen into that polynomial function and got back 23. Okay, so this one is actually the easier way to plug a value into a polynomial function, okay, rather than going through and directly plugging it in, okay, or substituting it in for that given the next value. This is called synthetic substitution. Synthetic meaning like kind of like fake substitution, but it is the quicker way of doing it, okay? The first step we want to do is write the coefficients of that polynomial function f of x in order of descending exponents, okay? So we're writing all the coefficients, meaning we got to make sure it's in standard form first, okay? If we're missing any exponents, so if it goes 4, 3, 1, 0 as exponents, we're missing that exponent too. So if we do that, we have to put in a 0 placeholder, okay, if that exponent was skipped. And I normally like to put little smiley faces in them, Okay, so placeholder for any missing exponent. Okay, then we're going to write the value at which f of x is being evaluated to the left. And we're going to use a big L chart for the synthetic substitution. Okay, so if you ever see synthetic substitution, you're thinking the L chart. Okay, step 2 says we're going to bring down the first leading coefficient. Then we're going to multiply on the outside that leading coefficient by the x value, and then write the product, so we're going to multiply them, and we're going to write that underneath the second coefficient inside the L chart and add them. Then we're going to keep redoing that, repeating, okay, all that for the remaining coefficients that we have, and then the final sum is the value of f of x at that given value for that polynomial. So if we try this, first we got to make sure, is it in standard form? Do my exponents go from biggest to smallest? Well, it goes 4, 3, 1, 0. Okay, so that's good. It goes from biggest to smallest exponent. Now we got to see, okay, am I missing any exponents? So 4, 3, 1, 0. I'm missing my x squared term, or my exponent of 2, right? So I know I need to put in a smiley face placeholder in for my x squared term. Okay, so what I'm going to do is put my x value out to the left, which is 3. Okay, now I'm going to line up my coefficients. So 2, -5. So my fourth exponent, my third exponent, we're missing the exponent of 2. So I'm going to put my smiley face placeholder in there. My exponent of 1's coefficient was -4. Then my exponent of 0 coefficient was 8. Okay, so at first we needed to just set it up. Now, step 2 said, okay, now we need to bring down our first coefficient. So I'm going to drop down that 2. And we're going to multiply on the outside, but add on the inside. Okay, so 3 times 2 is 6. I'm going to put that underneath my second coefficient there. Then add -5 plus 6, well, that's 1. And 3 times 1 is 3. I'm still adding 0 plus 3 is 3. Multiplying on the outside, 3 times 3 is 9. And if I add there, -4 plus 9 is 5. 5 times 3 is 15. And 15 and 8 make 23. And now I have to stop because I ran out of coefficients to add to after I multiply. So this tells me this is my answer. Okay, you got to box up, circle it, okay, something at the end, because if you don't, that doesn't really tell me anything, right? So at the end, your final number that you get, that is your solution if you were to plug it in directly, okay? So you should probably see by now this is a quicker way versus direct substituting in, okay? So, but you do get the same answer here of 23. Also in this section is being able to graph polynomial functions. Okay, so we're going to get to the graphing side. And when we go to graph polynomial functions, we need to pay close attention to the function's end behavior. Okay, the end behavior of a function's graph is the behavior of the graph as x approaches positive or negative infinity. Okay, the end behavior is determined by the function's degree and the sign of its leading coefficient. So we have 4 different kinds here. Okay, so if I look at the first type of end behavior, these are odds. Okay, so if my degree is odd, so like 1, 3, 5, 7, okay, really pay attention though to 3, 5, 7, 9, okay, those kinds of degrees, because remember our exponent of 1 is linear, so it's just a line. Okay, so if my degree is odd and my LC or leading coefficient's positive, okay, then my graph is going to look like this snake-like. That's how I like to remember it. Or snake-like or S-shaped curve, okay? And how I like to remember this as, since it's a positive leading coefficient, is a regular snake-looking kind of graph, okay? And if I look at the ends, I'm going to look at here and here, right? My ends. So as my x on my x-axis goes to negative infinity, that's what this means right here, my graph is going down forever and ever. And that's what this part right here means. So my graph is going down negatively forever and ever. But as x gets positive this way, forever and ever, or positive infinity, then my graph is going up forever and ever to positive infinity. And that's what this means right here. So we're paying attention to the ends of the graph. But what if I have a degree that's odd, but my leading coefficient or my line leader coefficient's negative? Well, it's still that snake or S shape, okay? But it's going to be a backward snake is like what I like to call it, okay? And again, I'm looking at my ends here on my graph. As x goes negatively forever and ever, infinity in this direction, okay, my graph is going up forever and ever, infinity, okay. Then as x gets positive forever and ever, okay, infinity wise, my graph is going to go down. So it's the flip-flop, down forever and ever, infinity. So there's the odd degrees. But what if we have even degrees, right? So these are what I like to call parabola-looking shapes, or these are either the U shape, okay? So if my degree is even, so 2, 4, 6, 8, 10, all that kind of stuff, and my leading coefficient or line leader coefficient is positive, then it's going to look like the U-shaped graph, okay? And if I look at my end behavior here, okay, this says as x goes this way, then my graph, or my polynomial f of x, is going up infinity forever and ever. And as x goes positively, infinity forever and ever, okay, then my graph is also still going up because it's a U-shaped graph. So my polynomial f of x is going up infinity forever and ever positively. But what if my degree is even and negative? Okay, so my leading coefficient's negative, but it's still an even degree. Then these are the hill-shaped kind of graphs because it looks like a hill, okay? And again, looking at the ends here, my end behavior as x goes negative infinity, my graph is going down forever and ever, my polynomial. And as x goes positive in this direction, then my graph is going down forever and ever. Okay? So that's what that means. So you're either going to have a snake-looking kind of graph somewhere, or the U/hill-shaped looking kind of graphs, depending on if your degree is even or odd, and positive or negative leading coefficient. So for example here, this is kind of a test prep kind of a question. What is true about the degree and leading coefficient of the polynomial function whose graph is shown here? Okay, so just by looking at that, it is a hill-shaped kind of graph, right? No kind of S shape or snake shape going on, and it's upside down like a hill opposed to the U shape. So that hill shaped, not shaded, shaped, okay, was for degrees that were even, and since it's upside down like a hill, that meant that the LC, or leading coefficient, was negative. Okay, and if we just match that up to our answer choices up here, that is D. Okay. In order to graph polynomial functions, we're first going to plot points to determine the shape of the graph's middle portion. Then we're going to use what we know about the end behavior to sketch the ends of the graph. Okay, so for example here, I have this polynomial function of a third degree because that's my highest exponent I got. So the degree is 3. And my leading coefficient is negative, right, coming from here, since it's already in standard form, it's a negative 1. And if I kind of think about My end behavior, my degree is 3, that is odd. So I know it's going to be a snake shape, right? And I know my leading coefficient's negative, so that tells me it's going to be a backward snake, kind of looking like this, if I were to graph it. And I were to throw in some axes there, okay? And how I'm going to actually graph that now is, well, I need to make a table of values. And it's always going to be good to plot in -3 through 3. That kind of gives you enough values to work with, okay? And on the calculator here, if you hit y equals and then type in your polynomial function, okay, and that X button is next to alpha, okay, if you need to know that. So you hit y equals, plug in, type in this whole polynomial function up top here. Then you hit second, which is the blue button, and then graph, which is the top right white button. So that was white button and the second button was blue. Okay, that'll pull up that table of values for you. And when you go to do that, at -3 it tells you it's 24. And at -2 the y value is 3. And then -4. And -3. 0, -1, and -12. And we could actually go and graph that now. Okay, so at -3, 24, it's obviously going to go clear off the graph somewhere. I'll put it up here. -2, 3, I could plot in the graph. -1, -4, 0, -3, 2, or no, 1, 0, 2 is -1, and 3, -12. Be right here, or it might be off your graph just a little bit, okay? So now we have all of them pointed. All we need to do is draw it like our backward snake, like we thought it was going to be with our end behavior here. Okay, so if I kind of connect them, it makes a dip and then goes back up and then goes back down again to make our backwards S shape kind of a curve. Okay, so there was our degree that was odd with a negative leading coefficient. And our last example here, we're going to do one more. So we got to think about, okay, what's our degree? Well, that's the biggest coefficient in standard form. My polynomial is already in standard form, or big is the smallest exponent. So my degree here is 4. My leading coefficient in standard form here, that is 1. Okay, so my degree, that's even. And my leading coefficient is positive. So that tells me it's going to be the U-shaped kind of graph, or parabola kind of looking graph. Okay, and again, I got to make my table of values. -3 all the way to 3. And from my calculator, after typing in my polynomial that I have to work with up here, and hit all the button strokes and pull up that table, my table tells me at -3 it's 76. 12, 2, 4, 0, -4, and 22. Okay, and now I need to graph that. So -3, 76 is obviously clear off the graph. -2, 12 may still be kind of off your graph, just a little bit, but make sure it's lower than the 76 one. -1, 2, 0, 4, 1, 0, 2, -4, and 3, 22, which will be off the graph. And all we need to do is connect them roughly. And here we have that U shape with the end behavior both going up forever and ever in the positive infinity direction, according to our end behavior of our degree and our leading coefficient there.